canonical ensemble. So I will tell you the difference of grand canonical and canonical. So as you remember, in the canonical ensemble, so in the canonical, the average of the energy is a constant, so sigma, for example, NR, ER. So this is one of the constraints on the system constraints. Well, but in grand canonical, not only the average of energy is constant, but also the number of the particles in each energy state is constant also. I will explain it. But before, I want to tell you one thing, is that, do you remember the method which I used in the last lecture to find the probability of the finding a system fixed at a temperature T, which is T is beta minus 1, kBT is beta. The probability, I derived this probability using the technique of the variation. We defined the entropy for the system minus Kb sigma PR ln PR. That's one method, or one thing else. I started from here, if you remember, Kb ln W ni. And for that, I used the counting method R from 1 to. And you know, we take the logarithm from this factorial and make the variation. So finally you get NR. So from here, as you remember, when you make because I want to use again this relation, so when you make the variation of logarithm accessible number of the accessible state in the system, which is equivalent to this omega, we call it density of the state, or logarithm is proportional to entropy. When you do that, I want to mention that that was proportional to this one sigma of delta NR somethings. 0, yes? But how you make the simplification? You use the Stirling approximation, huh? Always. Not always, you can do that. The problem is that I know that exactly the total number of the particle is a big number. I know that this is the Avogadro number. So for that, you definitely can use that. But the problem is that you have some state which a given number of the particle, which we don't know what, for example, I don't know, X factorial, one of this, some number of that, which is unfortunately is not very big number, is not large number. For example, unfortunately, you can have some part of the system with a little part energy and just with few particles. So what you can do that here, basically from the mathematical point of view, you cannot use the Stirling approximation when NX is not large number, only for large number. But from other side you have another N, which their number is big. So of course this one of them have problem, for example, is not big. But this is very good. For example, NY is very, very larger than NX and is in the order of the N. For that you can immediately use approximation. Just I want to tell you the problem, and I will give you the solution for this case, but I never will do go through the detail, because detail means a lot of information from the complex variable functions, complex analysis, and I don't want to spend time on that. Okay, to solve this problem, to be sure that when you use the Stirling, you are right or not, because some of the N, I told you, you exactly remember that, again, our first example, when you have even few level of the energy, just 3 level, and if you have a few number of the particle, some of the case you can just put 1 particle in 1 energy level, but another one maybe 4 in one of them. Even 4 respect to 1, of course they are in the 1 level, but anyway, when the number becomes, for example, 100 particles, so 1 in comparison to 100 is a small, tiny number. So I want to mention that this logarithm method is very good and working, and you can use this method without any problem since all your life. But the good, you know, because of this is tiny and this is like, finally it will get some type of the balance. I mean, some of the logarithm is wrong, and they are logarithm of the, for example, 5 just. Logarithm 5 is just number around 2, less than 2. But some of them have the logarithm of the, I don't know, 1 million. And 1 million logarithm is a big number. You have a small fluctuation in the n, and some of the n, and you have some large, almost all of are large, but you have also some, this is when you, this is actually, for example, I don't know, NAX, and for the other one, you have always the good approximation for any other one, I don't know, I just give the name to each one. For all of them, it's okay, just for the case that some of them have the lower number of the particle in the given energy, so you can use. So the best method is that the method of the, this is actually a complex variable method, saddle point approximation. So instead of the variational, the advanced textbook, they use the method of the saddle point approximation. Yes, I want to later bit explain that, what is that. As you remember, in the thermodynamic at equilibrium, actually, again I mentioned that the number of the state, or what you call it that, as this N, W, and I, just you needed to rewrite N versus the E. This always at the large number of the particle, you have many possibilities. So many possibilities that normally they are distributed over the Gaussian, always, always. Even if you don't know the energy level, even if you don't know the numbers, you can make even experiment. I mean experiment by the ball just in the box. I can give you that also, and just read the momentum or read the direction of the balls, for example, in the days. I mean any random system, even some balls in the box, billiard, for example. If you shoot the billiard ball, so it will strike the corners, yeah, and they will stay together. In this case, even if you want to count the number of the possibility, for example, that all the balls will reach, for example, this point, it's also a statistical problem. In this case, even if you do the measurement, you will see that it will be Gaussian. So Gaussian is always the one which you will see most of. Of course, we have some phenomena. They are called non-Gaussian. But most of the statistical system at equilibrium have the distribution of Gaussian. Okay, one thing I want to tell you that. Independent from the form of that, you will have this Gaussian. And this is the most probable state of the system, the most probable state. The most probable energy of the system. So, saddle point method is the method to consider any function near the probable, most probable value, or consider the function near the maximum variable of the functions. Basically, this said that, for example, if you have the integral like that, this is the integral, you know, it very much looks like the partition function, for example, when you have a sigma e, it looks very much like this partition function. Yes? Just this is the density of the state you set here and you convert this. Anyway, you are looking for the maximum of that, yeah? Or maximum of this, or maximum of logarithm something, but they are the same meaning. Logarithm W is just a number of the accessible state, and this is the same meaning of the D, and this is similar to the partition function. You can use the saddle point approximation, but I don't do this because we have more important things to talk. So just it remained, I was thinking to mention that the saddle point method is the general, more general, because just to make sure that you didn't use the Stirling approximation in the wrong way. Yeah, just that. But we don't do this approximation. We don't use it. So it's an advanced topic you can. Anyway, now today I want to talk about the system which almost they are the same as the canonical, almost. But the problem, the difference is that just instead of the fixing the energy in the system, you can have the another restriction. So you have a more index here, I mean. Here you talk about grand canonical. We have also grand canonical ensemble. So we started by microcanonical ensemble. Microcanonical ensemble was, let me just few minutes I review all. Microcanonical ensemble, what was from this point of the view? From this point of the view means that the probability of the finding of the any state is the constant. They are probabilities. Probabilities. States. All the states have the same energy. No, same probability of the finding. Microcanonical. So there is no restriction here. There is no any restriction. I mean, there is no any restriction over the energy or something. So for the canonical, as we find that the gives so PR, probability of the finding the system at the energy ER is exponential. When the energy of the system is constant. No constraint here over energy or other things. Okay, so you see a natural extension of this expression. It's possible to have another terms here, which is related to the, not only to the energy ER, it can be related to the number of the particles. So grand canonical means that the probability of the finding the system at the energy ER and with number of the particle, call it NS. Is proportional. I will prove that actually. It will be proportional to minus beta ER alpha NS. Two indices, yeah, you will have. Instead of the looking for the state with the given energy or with the desired value of the energy ER, at the same time you need to check that even if you find this state with energy ER, is it the number of the particle NS or not? If it's exactly the number which you want, you can tell that this is your desired state. This is what you are looking for. You know, and just I got this, and sigma can run from R and S. You know, 2 sigma actually. From the mathematical point of view, it looks like that you generalize a function from one variable to the two variables. Yeah. Here you have just one variable, the variable is energy, so if you change the energy, the property related to the state you will change. What is the properties? The probability of defining the system at the temperature. In my opinion, this is the only equation is important in statistical physics. Only that. Yeah, because before you don't, in any other discipline or course, you never can find information about defining a system with some amount of the energy at a special temperature. You never can get this information. You always have in quantum mechanics the problem of defining energy level, for example, or the problem of defining the particle in a special positions. Yeah? You make it the probability function, making the integral or something like that. So I have a different view about any equations here. So, and I want to share some of my idea with you. Maybe you don't like that and you want to keep it the standard definition. First, I want to derive this equation. The step will be exactly like what I did it for the canonical. So we write the W, we make the logarithm and variation, and finally we get this expression. And after that, I want to tell you that what I'm thinking about this small change in the days and how you can think about that. So, unfortunately, our whiteboard is not so big, so I need to, because some of the questions sometimes we need really to keep, but I don't know what to do. Anyway. In few minutes, we do just formal calculation to find this PRS or NRS, and you will see that. Anyway, if you remember, I want to conserve the time, so I use sometimes the papers. So we have the same. So LNW, NRS, which we call it density of the state, or we call it the number of the accessible state. Accessible states is the same, like the total number over higher N, R, and S. So NRS means number of particles. And by particle I mean also sometimes the visual particle. I mean, you don't need to see this particle. I mean, sometimes these particles are just hypothetical particles. Yeah. Any things which have a dynamics, I call it this particle. I mean, if you can write the Lagrangian or Hamiltonian for any things, it looks like the particle. Number of the particle or visual particle or with or at energy ER and total number of the particle NS. If you remember, in canonical, NR was the number of the particles sit in the energy ER. So here we have NRS 2 parameter. Because at the same time we need to fix also the total number of the particles. Keep it the average of the number of particles. So we needed to minimize that. Again, we have a constraint that NRS is E bar. And we have also the N bar. and you have the total number of the particles as a constant. Okay. I need to explain each equation because the equation which is new here is this equation. This equation is new. You know, in the canonical, you need just to control the temperature of the system. Temperature is related to the average of the energy, as you know in the strong fundamental physics. So always in canonical, you need to control the average of the energy or temperature. How to define that? Okay, to define the average of energy, you need to multiply the number of the particles which sit in each energy. This equation is easy to understand. What is that? At the same time, for any statistical system at equilibrium,